तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we shall continue our discussion on memories. Last class we introduced the CMOS memory cell. So, continuing on that, okay. CMOS memory would consist of the address inputs here, the X decoder, you have the driver, sorry, you have the driver, decoder, so these are the X address inputs, and from the output of the decoder you have a number of lines. Okay. So, if you have say 8 address inputs here, you will have 2 to the power 8 lines. So, this gives rise to 2 to the power 8 rows. Okay. So, I am just drawing the 2 rows here, and then you have the different columns. Okay. So, this is one particular column where you have the memory cell. The memory cell basically consists of, in a CMOS case, we have seen it consists of 2 pass transistors like this and 2 CMOS inverters connected back to back. Okay. The 2 CMOS inverters connected back to back. So, you have similar cells along this. Okay. And so, this is one column. So, I am just showing 2 rows. Similarly, you have other columns. Okay. So, you have again just exactly similar cells, okay, and here also. Okay. Now, what is done is when depending on the X address inputs, one of the output lines of the decoder goes high, and which selects the pass transistors corresponding to that particular row. So, all the cells in that particular row are selected. So, it selects one cell in each of the columns. One cell in each of the columns is selected, and that particular cell is connected to the data line. So, you have 2 lines actually, one is called the data and the other is the data bar line. That is because of this particular configuration here, you have an inverter. So, if one line is high, the other line will be low. Now, the next task is to select one of the columns. So, that is done again here using pass transistors. So, you have the IO lines, input output lines. So, so these pass transistors are connected to these IO lines. Okay, and this this input to these pass transistors comes from the Y decoder. Y decoder, which receives as input the Y address inputs, and the outputs are passed on to this gates of these pass transistors. So again, depending on the combination at the input here, okay, one of the outputs, only one output of the Y decoder is going to be high. So it basically selects one particular column. So only the output of one particular column is connected to the I/O lines. So depending on the input address, one row will be selected, which means that one particular cell in each column is going to be selected. So the information available on the data lines corresponds to that particular cell, and with the help of the Y decoder again we are selecting one particular column. So the output of that particular column is available on the I/O lines. So depending on the combination of the X and Y inputs, one particular cell is selected. So that is how it works. Now you can imagine that if we have a large size memory, okay, say for example if you have say 256K memory, bit memory, that means there will be 18 address lines, so 9 X address lines and Y 9 Y address lines, and there will be 2 to the power 9 rows and 2 to the power 9 columns. Okay, so 512 rows and 512 columns. So these address line, these word lines and bit lines are going to be extremely long, and they have large capacitances and resistances, and so there is going to be a lot of delay in charging and discharging these lines. So let us take a particular example. Okay, I will just draw the particular cell in a magnified form. So the cell looks like this. You have the inverters here, the CMOS inverters. This is one inverter, and you have, sorry, this is another inverter here. Okay, and what is done is this: in the cell, the output of one inverter is connected to the input of the other. So this is the cell. So this is VDD. This is ground. Okay, you have the word lines running like this. So you have the pass transistors which are activated by the word lines and which connect the output of this particular cell to the data line. So this is data line, say, and this is the data bar line. Okay. Now, so you have the word lines running all through the memory array. Now this word line is connected to the gate of the these pass transistors, and we know that in a MOS technology the gates are usually made of polysilicon. So these word lines are usually run on polysilicon. So in fact I would better draw it in this form, okay, to make it clearer. Okay, it is similar to drawing it. If this is the word line, this is the polysilicon word line, say, then I shall say this is the polysilicon word line. I'm drawing it in red to distinguish, and this is the data line. So the transistor is formed at this so this is the transistor and the gate is connected here. So this is the transistor. Okay. So basically what it does is when this word line goes high, okay, this data line is connected to the output of this cell. So this word line, okay, runs all through the cell. So it's a very long word line, okay, and a large part of the delay is due to the charging and discharging of this data line. So when the output of the decoder changes, then this voltage on the data line should change, and so the entire if the data line the word line is a large capacitance, so the capacitance has to be charged. So let us take a small example to see to find out the delays how to one may calculate. So let us assume take a small problem, okay, small memory, so 16K into 1 bit memory. Okay, and so array is 128 cells into 128 cells array. Okay, array size 1 mm into 1 mm. Polysilicon line, which is the word line, one micron wide, so that is a 1 micron line. Okay, select transistors, one micron, that is the size of the select transistors, channel length of 1 micron and width of 1 micron. Polysilicon sheet resistance is equal to 10 ohms per square. Capacitance to substrate for polylines, for polyline equal to 0.2 femtofarad per micron squared, and gate capacitance (4 femtofarad per micron squared). So, given these details, can we estimate the delay required to charge the word lines? Okay, so that's a small problem. Let us see how we are going to tackle it. Okay, first, the polysilicon line. This is a polysilicon line. We know the word line. The details about this is given. Polysilicon sheet resistance is equal to 10 ohms per square. For those of you who are not acquainted with this term of sheet resistance, see, a resistance of any line is given by resistivity, the length into the length divided by area. Now, if you have a line, if you look at the top view of a line, say this is the top view, okay, this is the length of the line, okay, and if this line has a width of W, okay, and if this is made of a sheet of material, you know, of thickness say T, if the material thickness is T, so suppose if you take the cross sectional view, okay, this is L, this is the thickness T, okay, and this may be the width W. Okay, so the resistance can be given as rho L divided by W into T. Okay, now this is the length, this is the width of the line, and this is the thickness. Now, if we assume a square, okay, if you assume a square here, one square of this material, then the length is equal to the width. If you take a 1 square of this material and length is equal to width, this becomes equal to rho by T, okay, that is the resistivity by thickness. So, if the thickness of the material is constant, then we can define a resistance for a square of the material. The important point to note here is that this resistance of 1 square of the material is independent of the size of the square. So, if you take the same thickness of the same material and you have a small square or you have a large square, okay, the resistance from one end of this line to the other it is the same irrespective of if you have a big square or a small square. So, it does not depend on the size of the square. So, in this case the total resistance is now going to be given by how many squares you have. Okay. If you know the sheet resistance, which is nothing but the resistance of one square of that material. Okay. So, the total resistance is going to be the number of squares. Since here you have 3 squares, so the resistance of this particular line is going to be the thrice the sheet resistance. Okay. So, that is how we determine the resistance of a line. Okay. Now, here it is given that the poly word line is 1 micron wide and the array size is 1 mm into 1 mm. So, it just runs for a length of 1 millimeter and it is 1 micron wide. So, the number of squares, polyline number of squares is 1 millimeter divided by 1 micron, which is 1000. So, poly resistance R say is equal to 1 millimeter by 1 micron. So, that many squares you have, the length is 1 millimeter, width is 1 micron. So, you have 1000 squares into 10 ohms. Okay. So, the total resistance of the polyline is 10 kilo ohms. Okay. Now, what about the capacitance? The total polyline is again 1 millimeter wide, 1 millimeter long, but it runs partly. If you look at this figure, this is the polyline, it is going to run partly on the field oxide, okay, which is a thicker oxide. So, it has a smaller capacitance and that is given by the capacitance to substrate of the polyline. The capacitance to substrate of the to substrate for the polyline is 0.2 femtofarad per micron squared. Okay. So, that is the capacitance for this part of the polyline. Okay. Whereas, where it is runs over the when it is a part of the MOSFET, okay, you have the gate capacitance, okay, which is higher because the oxide thickness is less. So, partly this polyline runs over thinner oxides which forms the gate and partly over thicker oxide for the remainder of the line. So, if you have a 128 cell into 128 cell array, there will be 256 such transistors. Okay. There are 256 such transistors because each cell has got 2 select transistors. So, and each transistor is 1 micron by 1 micron. So, the total capacitance is going to be polycapacitance, say C, is partly due to the gate capacitance. So, the gate area is the 256 transistors. Okay. So, 256 into 1 micron into 1 micron, that is 256 micron squared into for the gate capacitance is 4 femtofarad per centimeter square. So, 256 into 4. So, this is the total capacitance due to gate plus. So, 256 micron, for 256 micron it is running over gate oxide. For the remainder of 1 millimeter it is going to run on field oxide. So, plus 1 millimeter, so that is 1000 micron minus 256 micron, okay, that is the field oxide, into 1 micron is the width. Okay. So, this is the area into 0.2 femtofarad per micron squared. So, this is the total capacitance. Okay. So, the total capacitance is works out to 1.174 picofarad. Okay. So, this is the resistance and this is the capacitance. So, the total rise time, okay, estimated rise time if you have an RC type of if you consider just RC type of network is given by that is the time required to rise up to 90% of the final value is given by 2.3 RC. So, if you take this R and C, so this works out to be 27 nanoseconds. Okay. Of course, this is a rather overestimate, a very large overestimate of the actual delay, because this considers R and C separately, whereas this resistance and capacitance is distributed throughout the line. Well, if these are used as lump parameters here, but in actual practice they are distributed. So, if you use a distributed parameters, the actual delay will be around 15 nanoseconds. Okay. So, if you use distributed parameters, so this is much less than this 27 nanoseconds. So, T if you use distributed, so this is T R for lumped parameters. So, this will be around 15 nanoseconds. This is the actual value, 15 nanoseconds. This is gives a rough estimate of the delay by assuming lumped values of resistance and capacitance. That is one resistance and one capacitance. But since in actual practice the resistance and capacitance are distributed, one has to do a distributed analysis using distributed resistance and capacitance, where the delay, if one does such an analysis, the delay would be approximately 15 nanoseconds. So, this is the order of delay of this word line. So, this is an appreciable part of the delay of a memory cell, the time required to access a particular memory cell. So, obviously, we have already studied bi-CMOS drivers, and we know that bi-CMOS is capable of driving large capacitances. So, instead of CMOS drivers, we shall be using bi-CMOS drivers. We shall take it up when we look at bi-CMOS memories in the next class maybe. Okay. Now, so this is one aspect of the delay, that is charging or discharging the word line. Okay. So, we require large devices, okay, which are capable of or circuits capable of charging or discharging large capacitive loads, okay, to drive these word lines. Now, once we select the particular cell, okay, so suppose this particular cell is selected, then when we are reading this cell, reading the information of this cell, then the information stored on this cell should affect the data and the data bar lines. Okay. So, that we get the information regarding this cell on the data and data bar lines, and we are able to read the information of this cell. So, this means that this cell must be able to charge and or discharge this data and data bar lines. Now, these data and data bar lines also represent large capacitive loads, because they are also running all along the memory array, and these lines will be as long as the word lines. So, these data and data bar lines must also be charged, also constitute an important delay, can result in a large delay. Now, the problem here is that these data and data bar lines must be charged or discharged with the help of these transistors in the memory cell. Now, this since we know that, say for example, if you have a 256K memory, we have 256K such cells, and this memory array takes up the major chunk of the area of the total memory. Okay. And so, these transistors in the memory cell must be small size transistors, because if we are going to make them big transistors, then the area of the cell becomes very large. Okay. So, these transistors necessarily must be small transistors, because they take up a major I mean, if you just increase one transistor to twice the size, then the whole memory size is going to go up by factor of 2. So, one must at the same time one must make it these transistors small. At the same time, if you have small transistors, it is difficult to drive these the data lines, okay, using such small transistors. That is the problem. Okay. So, how do we solve this problem? Okay. The way to solve it is to use what are called sense amplifiers. Okay. The sense amplifiers will be used to actually charge or discharge the data lines. So, they are going to sense what is stored in the memory, okay, and based on that they are going to make the one of the data lines go high and the other data line go low. So, basically the charging and the discharging of these large capacitive loads, that is the data lines, are done by the sense amplifiers. And since we have we are going to have only one sense amplifier, for example, for one column, okay, so it does not matter, we can make them quite large transistors, we can use quite large transistors, because the number of sense amplifiers is going to be quite small. Okay, so for example, if you have again a 256K kilobyte memory, okay, so which means that 2 to the power 18 cells, okay, 256,000 cells, we have 2 to the power 9 columns. So, if we put one sense amplifier per column, we just have 512 sense amplifiers. Okay. So, 512 compared to 256,000 is quite a small number. So, we can afford to make these sense amplifiers quite large, and so that the data lines can be charged and discharged at a faster rate. So, what is done is, now instead of depending on the transistors in the cell to charge or discharge the data lines, we will use sense amplifiers to do so, and these can be made quite large. So, what we have is, we have here a sense amplifier, okay. For each column we have a sense amplifier connected to the data lines. Okay. Now, what is this sense amplifier? Let us see. Okay. The sense amplifier is also nothing but two inverters connected back to back. Okay. So, I shall just draw it in a magnified form. So, this is, suppose this is the data lines on which the cells are here. Okay. So, the sense amplifier consists of again two CMOS inverters. Okay. So, this is one inverter, this is another inverter, and the output of one inverter goes to the input of the other as usual. Okay. And these are connected to the data lines, this is goes to VDD, and the source goes to an input here, which is the sense input. Okay, and this goes to ground. Okay. So, this is a sense amplifier. Now, this is nothing but two inverters back to back. Now, if you have such a structure, okay, basically two inverters connected back to back, okay, if like this. So, this is one inverter and this is another inverter, and this is connected to two lines. So, you can have two possible combinations. Okay. That is, either this is 1 and this is 0. Okay. So, if this goes to 1, this will go to 0, and this 0 1, or you can have the other combination, this is 0 and this is 1. Okay. There are two possible combinations which are stable. Okay. Now, so if you have such a combination, it will always tend to go to one of these two possible combinations, and there is a large positive feedback involved. So, if it is in the if it is maintained in an unstable condition, it will always tend to go to one of the two states which is favored. Okay. Now, what happens is, if you consider this, okay, if we maintain these two the data and data bar lines at the same voltage, okay, data and data bar lines at the same voltage, and then if by some mechanism or some reason one of the voltages are changed by a small amount, okay. So, suppose this is V and this is V plus delta V, okay. So, this voltage is higher compared to this, then, and if we then turn on this sense amplifier, since this voltage is higher, so this will always tend to go to the higher value, that is VDD, and this one will go to ground. So, this one will go to logic 1 and this one will go to 0. On the other hand, if this is V and this is V minus delta V, that is this has a lower voltage here. Okay. So, what will happen is this will tend to go to this side will tend to go to 0, whereas on the other side, which is a higher voltage, will tend to go to 1. So, because of the large feedback, positive feedback here in this circuit, okay, any discrepancy here between the two voltages is going to be magnified and or amplified, and so one line will go to 0 and the other line will go to 1, and this configuration will go to one of its two possible steady states. So, this sense amplifier is included in this cell here. The other thing which is done is, so what we must do is we must initially have equal voltages on these lines. Okay. So, what we do is we do a pre-charging. So, both these lines, the data and data bar lines, are maintained in the pre-charged condition. So, what we have is here a pre-charged circuit, okay, which is nothing but two transistors here. Okay. Say these are two PMOS transistors, okay, and here you have a voltage Vp, which is the pre-charge voltage, and this is the pre-charge line. So, again it is a two-phase clock is used. So, when the pre-charge input here goes low, okay, when the pre-charge input here goes low, these two PMOS transistors, they turn on, okay, and this pre-charge voltage here, which is available here, is now available in the data and data bar lines. So, the data and data bar lines are both pre-charged to this initial value Vp, okay, pre-charge voltage. Okay. So, when this pre-charge value is input is low, then both the data and data bar lines have the same values. Now, when we select a particular cell, the word line goes high, a particular cell is selected. Now, when a particular cell is selected, okay, what happens is, as we said, it can be in one of the two possible combinations. Okay, that is either if you look at the cell, all right, which is nothing but again two inverters connected back to back. So, if this is a cell here, okay, so if there can be only two possible combinations. In one combination, if this is logic say 0 and this is 1, okay, then it means that this transistor is on, NMOS transistor is on, and this is off, and here if this is 1, it means this is on, PMOS is on, and this is off. So, this is one particular combination. So, if this is the particular combination, what is going to happen is this line, because the NMOS transistor is on, tends to get discharged through the on transistor. So, this voltage here on this line is going to tend to get reduced, whereas this line, this PMOS is on. So, there is going to be a charging current, and this voltage, okay, this data line here tends to get charged up. Okay. So, if this is the condition of the cell, okay, then what is going to happen is one line is going to be pulled down, okay, and the other line is going to be pulled up. So, there is going to be a small difference, okay, in the voltages between the data and data bar lines. So, suppose the data and data bar lines charged to Vp, okay, and then one line will go above Vp, this way go below Vp this side, and this one will go above Vp. If the state of the cell was different, okay, then it would be in the different direction. Okay. So, depending on the state of the cell, okay, a voltage difference is created. Now, then what happens is the sense amplifier, okay, the sense amplifier is turned on. Once the cell, once the difference in the voltage, a small difference in voltage, see, because the cell uses small transistors, so it will take a long time for any large appreciable voltage difference between the lines to develop. So, when a small difference in voltage is developed, say 0.1 volt or so, the sense amplifier is turned on. Okay. So, if this is a sense amplifier, okay, so when this transistor is turned on, okay, this sense amplifier is activated. If this is off, the sense amplifier is off. So, when this sense amplifier is activated, okay, when this sense amplifier is activated, what happens is this is again going to go to one of the two states. So, when if there is a small difference, initial difference, say this is Vp plus delta V, and if this is Vp minus delta V, okay. So, this voltage being larger than this voltage, Vp plus delta V being larger than Vp minus delta V here. So, there will be a tendency for this voltage to go up to VDD, that is the high voltage, and this voltage to go down to ground. Okay. So, depending on the initial state of the data and data bar lines seen by the sense amplifier, okay, one line is going to go high and the other line is going to go low. So, depending on the information stored in the cell, okay, one line is going to go high and one line is going to go low. So, that is how the sense amplifier is used to speed up the operation of the charging. And since this is a big transistor, these are big transistors, they can charge or discharge the data lines faster compared to the small transistors. So, basically again just to go through the operation of this memory, okay. So, what is done when you are reading, okay, X address and a Y address, depending on the X address and the Y address, a particular row is selected, okay, and a particular column is selected. So, when a particular row is selected, the cell is connected to the data lines, okay, and this is going to change the this depending on the configuration or the status of the individual transistors in this cell, okay. The data and data bar line voltages are going to change. The data and data bar voltages are kept at a pre-charged value, they are equated initially, okay. So, one line is going to go up by a small amount and the other line is going to go down by a small amount. This is then once a small difference is created, a sense amplifier is turned on. It is important that the sense amplifier is not turned on right away, because what happens is if the sense amplifier is kept on initially, then what happens is due to some noise voltages, the sense amplifier may tend to go in one of the two directions, okay, making the data line go to one of the two high or low directions. So, once the small difference in voltage is created due to the cell voltage, the condition of the transistors in the cell, then the sense amplifier is turned on, which makes the data, one of the data lines go high and the other one go low, and then one of the columns. So, this happens in all the columns, because one cell is selected in all the columns. Now, due to this configuration here, due to the presence of these pass transistors, okay, and the Y decoder selects only one of the columns. Okay, one of the column is selected, which is connected to the input output lines, and the information on that particular column only is passed on to the IO lines. Okay. So, for writing mechanism, okay, what is done is these IO lines can be used to write information into the cells by forcing voltages on these data lines. So, if one line is made to go high and the other line is made to go low, then you basically can write into these particular into a particular cell. Okay. So, so this is how a CMOS memory cell is going to work. Okay. Now, we shall see that the CMOS, okay, we have already seen that the bi-CMOS, okay, has certain advantages over CMOS, okay, and this is especially in the areas of driving large capacitive loads. And here we have seen that we have seen it as an example that the word line has a large capacitance, and so for example a bi-CMOS can be used to drive these large word lines. So, in fact, the bi-CMOS can be used in a number of areas in this memory, the static RAM cell which we have discussed. Okay. Now, so in fact BiCMOS memories have become quite popular, and they have much improved performance when compared to the CMOS memory. Okay. Now, we shall take up the case of BiCMOS static RAM and see the particular areas, okay, where you introduce bipolar transistors, the particular to speed up the operation of the particular static RAM. Okay. Now, it is not that in a when you have BiCMOS technology available, you would introduce bipolar transistors into all areas of the static RAM. Okay. We will have to introduce this bipolar transistors judiciously in certain areas. Now, if you just look at the block diagram of the static RAM, you have the X address inputs, the driver, decoder, then you have the memory array, memory cell array. Okay. And then you have the sense amplifiers, okay, and then you have the Y decoder, and okay. Now, so these are the Y inputs here. So, in fact, you have in BiCMOS usually the interface circuits are the bipolar circuits. So, you have buffers here to convert the voltage levels from the for example, if you are using ECL interface from ECL to CMOS. So, you have a Y buffer, and you will also have an X buffer here. Okay. So, I will put X decoder driver, Y decoder driver, and you have the X buffer. Okay. So, this is the block diagram of the memory array. Okay. Now, let us see which areas what would you use. Also, you have some control circuitry. Yeah, you have some control circuitry here, okay, which actually is required to choose whether you want to do a read operation or a write operation, and then you have the outputs coming from the. Okay, so you will have output buffers. Okay. Okay. Now, so this is this control is going to. Okay. Now, for this, which technology would be used in which regions? For example, if you take the memory cell array, okay. Now, this memory cell array constitutes the major portion of the device of the cell, okay, in terms of area. So, this has to be in a technology which consume less area. Also, since the maximum number of transistors, okay, are in this memory cell array, the power dissipation, the total power dissipation of the cell is going to depend on the power dissipation of the memory cell array. So, this cell, okay, has to be made in using such a technology which has low power dissipation and has less area, takes up less area. So, this memory cell array is basically done using CMOS. Okay. So, the memory cell array will remain CMOS in BiCMOS memory. Okay. So, this is CMOS. Okay. So, the memory cell array even in a BiCMOS is going to be a CMOS. So, we do not introduce bipolar transistors in the memory cell array, because the bipolar cell takes up a lot of area, and also a large power the power dissipation is going to go up. Okay. So, what we are designing is for a large memory, okay, So this would still be a CMOS. Okay, we know that in ECL, for example, if this were made of ECL, then the power dissipation would be quite quite a lot, and so we cannot afford this in a large memory. Now, what about these decoder drivers? These decoder drivers would be using BiCMOS, okay, because these have to drive very large capacitances, and we have already seen that this BiCMOS is capable of driving large capacitance. Okay. So, we make this Y decoder driver also using BiCMOS. So, this is the symbol for BiCMOS, that is we basically use BiCMOS gates, okay, to drive these large capacitances. So, this will be the decoder driver will be driving the large the word line capacitances, and also the Y decoder driver has to drive large capacitances. So, these are basically the BiCMOS. The sense amplification, in this case the sense amplifier usually in a BiCMOS memory is done using bipolar transistors. Why? Because bipolar transistors, we have already seen, has a very large transconductance, much larger compared to their CMOS counterparts, and that is used to sense this used for sensing in this memory. Now, a small voltage, okay, a small voltage can be sensed much easily, okay, much more easily using bipolar transistors. Okay. A small difference say of less than 100 millivolts can be sensed by a bipolar transistors, which will result in a large change in current, which is not true in the case of MOS transistors, because you require a large difference, a much larger difference in the gate voltage to be really sensed. So, because of the this is because of the larger transconductance in bipolar transistors. So, bipolar transistors are generally used in this sense amplifiers. So, this is completely bipolar. Okay. So, just keep this bipolar. So, there is blocks like this is a bipolar. Now, the control again has a combination of bipolar and CMOS. So, this can be BiCMOS. Whereas this outputs buffers in general, because these are supposed to be high speed circuits, okay, many of these BiCMOS memories use ECL logic levels. Okay, the input and output levels are ECL. So, you require buffers to convert these levels into the standard CMOS levels, because you see the memory cell array is actually using CMOS. So, what is done is it has to be converted to CMOS levels. So, in fact, here you have negative voltages. Okay, ECL level is negative voltage if you are using an ECL level, okay, and this has to be converted, and this has to work in a CMOS environment here inside. Okay. So, what is done is you have negative voltages, but it is still in a CMOS type of levels, that is, suppose if you want 5 volt memory. Okay. So, this is converted into say in a BiCMOS, you know that the output is going to go to VDD minus VB to VB, which is the lower level. So, if 0 is going to be VDD, okay, you can represent 0 voltage as VDD, and minus, you have minus VSS. So, in fact, the voltage levels internal to the circuit can be minus 0.6 to minus say 4.4. Okay. So, this is minus 0.6 is considered logic high, and whereas minus 4.4 is considered logic low. So, basically the CMOS is going to operate in the same way. It is just a level shifting down to a negative voltages. Okay. So, in this case the memory, okay, so you have the full swing. If you have 5 volt, you have a 5 volt full swing for this operation of the memory cell array. So, only the voltage levels would be negative instead of positive. Okay. So, 0 volt would be high and minus 5 volt would be low. Okay. So, what we shall do in the next class is we shall study in detail BiCMOS static RAM, okay, and see how it is realized in the how a static RAM can be realized or is realized in the BiCMOS environment.